Hello and welcome to Toddcast number 20. This will be focused on the third of the three perspectives we draw molecules with. There's a side perspective, which is the bond line, which will include dashes and bold wedges to represent coming out of the plane or into the plane. There is the Fisher projection, what we've discussed, and then there's the Newman projection. So Fisher is a top view, Newman is a head-on view. And so by looking at the different perspectives, you have a better idea of how the structure is situated. And then within that, we'll also be able to emphasize steric hindrance, where groups start to run into each other's space and the impact this has on the molecule's reactivity and stability. So need to start by just going over what a Newman projection is. And so again, when I look at a molecule, there's different perspectives. So I'm going to draw a molecule here, and we'll just come up with the different ways we can draw it. So let's say I have an H going back, an OH coming out, an H coming going back, and let's say a Cl coming out. This is my side view. I'm looking at the side, so I know where things are relative to one another. Now, top view, the Fisher projection sort of scrunches it in, but the Newman projection is the one that looks from this perspective. My eyebrow will be there this time. And so if you do this, if you look straight down this bond, you will not be able to see this. And so it's kind of like if you put your thumb in front of something, it'll block it a small amount of whatever's in front of you. But if you put your thumb in front of you, something that goes further and further back, the view gets blocked even more. So this carbon is going to create a blockage in your view from about here to here. So we see the front carbon just fine, the nucleus, but we're blinded. We have a blind spot. It's fairly large on the backside. Okay, so that is the perspective we're going for. Hopefully that helps picture-wise. But to draw a Newman projection, again, you want to look directly down a carbon-carbon bond. So doing the same kind of structure, except I got rid of the Cl and the OH, so it's a little more simple. I only have to focus on the CH3. So looking down here, and again, eyebrow on top to notice which I'm going to call top, which I'm going to call bottom, and front and back. So I will not be able to see the back carbon. So the front carbon is represented by a circle, or dot, excuse me, the back carbon by a circle. So if this is my carbon, again, that's my blocked view. So I cannot see the back carbon. So on the front carbon, I have the groups, I can actually see them coming off the carbon. It's going to draw this bond straight down like this, representing that CH3. This one is coming out, which if I put out my hand, it'd be on my right side, coming out and going up slightly. And then this one's going back and also going up. So behind the plane, so to the left, and up, so it's pointed up. In the back, again, I cannot see the carbon itself. So the circle represents the blocked portion. I cannot see it, so I just draw a circle. But I can see the CH3 sticking up. I can see this H here going down and into the plane here, so down to the left. And here, looking from this side, it'd be going down and to the right. So I'm going to color coordinate it. This is on the front carbon, so that's this one. This is coming out, so it would be this one. This is going back. So that's this one on the front carbon. As far as the back carbons go, the CH3 is sticking straight up. So this one's going back. So this one, and finally this one's coming out. So that's this one. So hopefully you can see this color coordination. That helps. Okay, so the CH3 sticking up, the H on that one, the H on that one. And then in front, this H is going to be on the blue, this H on the green, and this CH3 on the purple. So draw the front substituents, back substituents, and then you're done. You've done it. So it's a victory dance time. And if you can't dance, then do a victory wave or a victory nod or a victory fist pump or something because you did well. We're going to take this structure and now start considering what happens if the molecule starts to rotate, twist, contort in any way, how this will be affected. So, but first things first, we now know how to draw a Newman projection. Now, Newman projections, we use them because they show orientations in different groups. So even though this is on one carbon right here, the CH3, and the CH3 is on a back carbon, the circle one, they still can bump into each other. So if I go back to the drawing from before, my CH3 is up here, my CH3 is down here. But if this were to rotate out of this position and come up to here, and if I were to actually look more carefully at the H's, so make the CH2H and then focus on the one H here, those two H's can actually get in the same spot. So that's where it's going to be steric hindrance, two atoms trying to be in the same spot at the same time. And because of that, the groups will want to try to get away from each other. You don't want to bump into each other. You spread things out as best you can. So this overall is referred to as a staggered structure. So staggered refers to the overall molecule where I can see the front three substituents on the front carbon and the back three substituents, back three groups on the back carbon. They are not being blocked, so they are staggered, they're offset. So this one's here, this one's here, and this one's here, and the other ones are offset, they're between those. The second half of the term is anti, refers to the alignment of the bulky groups, so the groups I'm interested in, the two that could bump into each other. The CH3s are said to be anti-paraplanar. So what that means is they are in the same plane. Paraplanar means one is going one way, one's going the other, anti. So they're opposite of one another. So anti for short. So we refer to those groups being anti, and they're opposite one another, and the overall structure is staggered. So like this one, the CH3 is in the same plane but going up. This is the same plane but going down. They're anti-paraplanar or anti. Okay, front carbon, red dot. This is my CH3, so I'm just going to draw red for that, green for that, and blue for that one. Planar up, straight up and back. Right and coming down, out and down, and then left and down, in and down. Okay, that's the front carbon. The back carbon, I'll choose the same color scheme. Red for straight down, green for in back, blue for in front. So red straight down. The blue here is coming out, but on the back carbon, green is going into the plane, so it's going to appear on the left. So we draw a circle for the back carbon. That's this circle here. So a dot for the first one, circle for the second. One straight down is planar and down. The one that's going to the left, the one going in, and the one going to the right is the one coming out. So out and up is right and up in this perspective, and the one that is in and up will be left and up. Okay, so it's just making sure you can recognize where things are relative to one another. Okay, so if this molecule would rotate, so like mentioned, if these groups can rotate around, so the front carbon stayed put, but the back carbon, the groups on there rotated up, this CH3 then rotated 120 degrees up to this position here. So now they're closer. So you can still see the back substituents and the front substituents. So overall, it is still staggered, but they're no longer anti one another, no longer the same plane. So they refer to this as gauche. So this alignment, I will do, I guess, emphasize it in yellow, is known as gauche. You're going to hear a term called the dihedral angle. That is the angle when squished into this structure, 30 degrees apart dihedrally. So when I rotate around, 30-degree rotation would have it get eclipsed or blocked. So 180 degrees away in anti, 60 degrees away in gauche. So the structure, same thing as before. We have front carbon with the back H, the out H, and the planar CH3. Same thing, the planar CH3, CH, and this. But now what's different is the CH3 is now on the right because it's coming out. And then this group is an H down, and this group is that going right back there. Okay, so planar up, straight up. And this time, right and up for the CH3, out and up. And I'm only going to consider this time the bulky groups, the ones that I'm focused on in terms of anti and gauche. And so now I'm going to rotate this. So if you try to figure out how you went from this structure to here, note that the front carbon is still CH3 up and H is here and here. So it didn't rotate. If the back one rotates 180 degrees, the CH3s block one another. You cannot see the carbon from the carbon, can't see the H from behind the H, same thing. So it has been blocked. It is an eclipsed structure. And then the term we're going to use is syn. When they're on the same side on a double bond, we call it cis. When they're on the same side of a sigma bond that can rotate, we call it syn. So sure, it's somehow related to the word synchronous or synchronized or some sort of togetherness, but they are syn together. Okay, so let me pick a color for that. I guess I'll choose red this time. So those two groups, they block one another. They are syn. And overall, the structure is eclipsed. So that is when you run into trouble. That's where this group right here can interact with that group right there. So that's when you have issues. So eclipsed is the least stable because the bulky groups can run into each other. Anti is the most stable because the bulky groups are far apart. So when you're dealing with steric hindrance, two groups that don't have any favorable interaction, they just bump into each other, then you want them as far apart as possible. Anti is your best. So in front, it's planar up, and in back, and planar up as well. So in the plane and up. Okay, so a lot going on. First time seeing it. Hopefully you can take it all in. So we want to actually look at the rotation. So this is called dihedral rotation. Wherever you start, if you go 120, you have another of the same type. So if you start staggered, that'll be staggered. Start eclipsed, it'll be eclipsed. And if you go 360, it will go all the way around. So we're going to start with this structure. And because everything's H, I can't really label anything specifically. So I'm going to randomly pick this H on the front and this H on the back and call them anti to begin with. Anti and staggered is my most stable conformation. So that's going to be low on the energy diagram. As this rotates around up or this back one rotates down, whichever way. And that's the beauty of it. One thing rotating clockwise gives you the same result as the other one rotating counterclockwise. So it's irrelevant which one you say is rotating, but I want to leave the front carbon as is and rotate the back carbon. That's just kind of the habit I have. And I've chosen to have this one rotate, the back carbon rotate in a clockwise fashion. So when it rotates 60 degrees clockwise, the back carbon, that H will get there, that H gets there, and that H gets there. So it is eclipsed. So if you can barely see the H behind it, it's blocked. There's no anti or gauche per se because everything's the same atom. But these substituents will be syn with respective H's, but not necessarily to each other. So the energy goes up because it is eclipsed. So staggered, most stable, eclipsed, least stable. If it continues the rotation, though, it's going to come to 120. So again, like I mentioned, 120 is going to get it back to where it was. So now you have the same thing here, only the identified H's, the labeled H's, the marked H's are now close together. They're gauche, but it is this exact same energy. When you rotate another 60, you now have another eclipse. So it goes up to the same energy. When you rotate yet another, this Blue one's down and free. It's a staggered structure. It's back to stable. When it rotates another 60, it's going to be up and blocked, and then finally back to the lower level. So you start and finish with the same structure, and you go from a staggered to eclipsed, back to a staggered, back to eclipsed, back to staggered, back to eclipsed, back to staggered, where you started. So this whole full bond rotation, 360 takes you all the way around. This studies the energetics of that process. So when it's all H's, it's kind of boring. When we have ethane, when we start doing groups like propane, butane, ones that have not all H's, then the energetics will fluctuate a little bit. And so we're going to go into more detail with future examples. So this is about as simple an example as you can get. H is everywhere. So steric hindrance is minimal. I've left it unmarked, but we'll go into roughly how many calories, kcals per mole that ends up being with some future examples. Okay, so if this is 0, this is 12, that would mean that's a 12 rotation. But if they're bulkier groups, it might go up to 18, 19, 20, and it might only drop to, let's say, 4. So for now, these energies I put in there, that's just for ethane. So what I can conclude from this is when it rotates into this structure, and this structure, you have 1, 2, 3 eclipsing interactions. So 0 to 12 is a gain in energy of 12 kilojoules per mole. And if you have 3 of them, 12 over 3 would be 4. So I'm going to conclude each of these H's is going to be 4 kcals per mole. So if that makes any sense at all, if it's 12 kilojoules per mole that we have to add to do it, it's because it's 4 for each of these individual interactions. And so in chemistry, we like to log the energetics of how much energy it takes to do things. So we can predict what's going to happen under certain temperature conditions, what temperature gives it enough energy to make it happen, not make it happen. So we can control the behavior of our molecules by changing the temperature and allowing it to rotate or not rotate, which ultimately will affect how reactive it is. Okay, so lots going on here. You have to draw a Newman projection, and then you have to visualize rotating around. So when we look at that bond rotation energy diagram again, but this time, a more complex molecule. We're going to do butane this time. So butane, you have CH3s, so now a little more energy is going to be involved. CH3 is a bulkier group, so it's going to run into things more. So its steric hindrance, its repulsion energy is going to be increased. So whatever I start here, I'm going to go up to this structure. And so you'll note this is anti, everything is gauche. But when I rotate 90 degrees, and again, I'm rotating the back carbon by 60 degrees. So that's going to go to there. This group is going to go to there, and that group's going to go to there. So you end up with the CH3 in back, eclipsed. You're going to end up with an H. So you now have an HH eclipsing, which we knew was 4. And you have these, which are more than 4. So if it's 4 plus a number bigger than 4, a number bigger than 4, then it's going to be overall bigger than 12. So I'm going to use that to accrue information. When it comes back down, you'll notice it doesn't go to the same low level because anti is more stable than gauche. So gauche interactions still cost you a little bit of energy. And so if I can compare how much this compared to this is, that's my gauche anti difference. That'll tell me how much a gauche interaction cost you. So if I consider it, there's a CH3 anti to an H, anti to an H, CH3 anti to an H, anti to an H, and then HH or gauche as well. I'm sorry, gauche, 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 and 2 H's. So 4 CH3 to H interactions that are gauche, 2 HH gauches. This one will have 2 H to CH3 gauches, so not 4, and it has 3 HH gauche interactions, but the big one is a CH3 that is gauche. 2 CH3s, that gauche interaction is going to add instability to the system and make it a higher energy. Okay, notice this becomes key. If I keep on rotating around, CH3 is going to go 60 degrees to there, 60 degrees there, and 60 degrees to there, which ends up having it eclipsed. This is now blocking it. That's massive in energy. 2 very bulky groups, that's going to be the hardest thing to go overcome. So again, you'll notice that when a CH3 is eclipsing an H, CH3 eclipsing an H, it's here. But over here, it goes all the way up to that energy level. Comes back down. This is kind of the same thing as this. You have a gauche CH3CH3, two CH3H gauche interactions, and then three HH gauche interactions. So the energetics are the same here. When it comes back up, this structure is also equivalent to this one. H and CH3, H and CH3, and then two H's, same thing. So symmetry and energy, it comes back down to the original structure. So it's still symmetric because the molecule is symmetric, the graph is symmetric. So the previous one, everything the same energy. This time, a little bit different. So we're going to call that our 0 point. This one's actually 19. So I know when it's HH, this is 4. So if that's 4, 19 minus 4 is 15 left over. So these must be about 7.5 each. And then apparently your gauche interactions, about 3.8-ish. Okay, so what I conclude then is if this is 16, then the extra eclipsing CH3CH3 must be adding 3 additional kcals per mole. Okay, so a gauche CH3 interaction is 3.8 higher than anti-HCH3 interaction due to steric strain. Okay, so I must be able to see that right here, check. And then 2 CH3 or HCH3 eclipsing interactions and 1 H eclipsing interaction is plus 16. So that one is this one right here is 16, not 19 here. So this, in this case, is one I should be looking at, 4. And then 16 minus 4 is going to be 12 divided by 2, be 6 for each of these. And then this one is the one that adds the extra 3. So forgive me for my previous statement. So let's do some math. So based on the energy diagram and conformations of butane and using the energy cost of eclipsing CH bonds, determine the energy required to eclipse a CH bond with a CCH3. So figure out what this is. So that's the math we just did. So 16 is what we just learned for this overall structure from start to like fully anti to this group. So to fully rotate it 120 to get it here. So 16 kcals per mole. Before, we knew it was 12, so each of these were 4. So this one is 4. We had that from our first experiment. So again, we have 12 kilojoules per mole left over. 4 is accounted for here, so 12. These are equal. So minus 4 is 12. Divided by 2 means 6 for each. So hopefully that makes sense, that the math is working out. So 6 kilojoules per mole for each of those. That accounts for the starting from 0 and going up to 16 would be having to increase by 4, 6, and 6 for a grand total of 12. Okay, so there's a little math in OChem. It's not bad, and hopefully it makes some semblance of sense. But this is how we study what different interactions cost us. And then we can make a prediction of what an overall structure, how stable it'll be compared to other structures based on these interactions. Okay, so now we're going to determine the strength of an eclipsing group. So these I know are 4 and 4. Overall, this is 19. So that's from the graph. 19 minus 4, so 19 minus 8 is 11. So it's substantial. The amount of energy that you end up spending to get the 2 CH3s is 11 kilojoules per mole. So eclipsing interactions, when they are thin like that, very, very strained. So you do not want to have a structure overall eclipsed, and you don't want to have your bulkiest groups syn to one another. Okay, so hopefully the math is reasonable. Okay, so time to look at how these things work. And just to give you a heads up, I like to throw just learning-based questions. So we're not looking for an answer, we're looking for the logic of how we get there. So the most stable, I know, is going to be eclipsed. So first off, let's eliminate timeout, not eclipsed. Must be staggered. So let's eliminate all the eclipse structures. Staggered, 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 staggered. That one's out. Okay, next, consider the bulkiest groups. CH3, because it's 4 atoms, is bigger than NH2, which is bigger than OH. So I should consider the CH3s. I should have them as far apart as possible. So here they're gauche, here they're anti. Okay, so hopefully that seems reasonable. So that would get rid of then choices A and B. You want to have the biggest groups furthest apart. Here's where I've gotten tricky with you. And I just want to emphasize this early in this process, and that is steric hindrance is a repulsive condition. So if I'm worried about size, then I want the next bulky groups far apart rather than close together. If you only worry about repulsion, but what happens in this case is, yeah, they can repel, but also you can form an H bond. So the lone pair on N can form an H bond to an O. If they're far apart, it can't happen. If they're nearby. So attractive forces are usually, like hydrogen bonding is anywhere from 4 to 8 kcals per mole. Gauche interactions are rarely above 2. So even though this is gauche, also a bit extra energy for gauche, the H bonding makes up for it. So you have to worry about steric hindrance for bulky groups like CH3s, which don't want to be near each other. But you have to worry about attractive forces. So your most stable structure is actually choice D. So right out of the gate, giving you a trick question, if you want to call it that. But I don't know if it's a trick question as much as don't focus only on the small piece. You have to keep building. So the small piece we've learned is repulsion of bulky groups. But we also learned in previous lectures about intermolecular forces like polarity, hydrogen bonding, and London forces to a small extent, but not in this, they aren't that significant. We typically ignore them. But polarity and hydrogen bonding definitely play a role in how things go into the most stable conformation. So D, most stable. Okay. So let me get rid of that. I will keep that here, but this is the H bond we're talking about. So the OH can hydrogen bond with the lone pair on nitrogen. Not bad. So sorry to end with a trick question. This is one of those lectures that we did a lot of stuff really fast. Make sure you understand things in slow motion, and it is worth your time to sit and draw out all of those structures at 0, 60, 120, 180, and force yourself to just look at the energetics of it and just an overall rundown of how it works. So that said, we have reached the end of yet another Toddcast. So I will see you at the next Toddcast. Bye.